Hello, this is section 1.5 for Calc AB, and today we're going to be talking about infinite limits. Now, just to warn you, infinite limits, I believe, are going to be your most challenging limits because they're so easily disguised amongst your other ones that can be used by plugging the number in or simplifying the function, or maybe it's a special trig limit. But in these cases, oftentimes you might have to think of it more of as a numerical approach instead of solving these analytically. So just to refresh your memory, so use math to explain why the limit as x approaches 2 of this rational function does not exist. And you can already see there's an asymptote at 2. So anytime there's an asymptote, the limit does not exist. Now you might say, Cogswell, we answer with infinity. That's true, but remember infinity, that's down here. Note, the limit as x approaches c of f of x equaling infinity does not, the limit exists. You're just instead telling me how it fails to exist. All right, so let's jump back up here. So a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Now remember, in the last section in 1.4, we did limits off to infinity. So that's your horizontal asymptotes. Today we're talking about our vertical asymptotes. So determine whether the limit as x approaches 5 from the right of this rational function approaches infinity or negative infinity. So you can either graph the function, you can use a table, but notice ultimately you're not going to be able to plug 5 into that function. We can't simplify this function to plug 5 in. That's the key. All these other ones we've done so far, we've been able to ultimately plug the number in. So in this case, either looking at the graph or plugging in numbers from the right that are getting closer and closer to 5 to tell us what's going on. And you can see this is exploding to negative infinity. All right. So again, vertical asymptotes are what we're dealing with. We're going off to infinity or negative infinity. Okay, so this big section right here, excuse me, are just functions where we can practice your vertical asymptotes. So setting the denominator equal to 0 after you have simplified your rational function. Because remember, if things cancel like it happens in E, that becomes a hole in your function. Okay. Looks like there's a mistake there. It should be a negative sign. Okay, so correct your notes. That's why we watch the videos. Okay. So, but otherwise, if you look through these functions, so tangent of x, that has infinitely many vertical asymptotes, and because when cosine of x equals 0, and that's what this is, n representing an integer. Then for b over here, first try to simplify, you'll notice it does not simplify. So you get 2 vertical asymptotes, and that's okay. Now d is a little tricky because if you graph this one and you zoom in at 0, it actually exists. It's approaching a number. So if you're clever about it, tangent turns into sine of x over x. The limit as x approaches 0 of this function is actually 1. So then you're left with 1 over cosine. So that cosine of x is what you're actually setting equal to 0, which is what we did in the previous problem. So that's going to be your vertical asymptotes. But note, there is no vertical asymptote at x equals 0. So that's an interesting one. That's a good one to graph. Okay, and then down here, this is a pretty straightforward problem. Nothing cancels, so it's just -1 and +1. Right? So just that's totally review. Slightly harder problem here, but hopefully review for you when the denominator equals 0 after you have simplified your function. Okay, so let's get into the limits. So properties of infinite limits. So let C and L be real numbers, let F and G be functions such that limit as x approaches C of f of x equals infinity, but notice the limit as x approaches C of g of x equals L. All right, so the limit actually exists for g of x, but does not exist for f of x. So sum and difference, so the limit as x approaches c. Remember, when you're adding and subtracting, you do the limit of the first function and then the limit of the second function. Those are separate, and then you add the value together. So f of x as you approach c is infinity, remember, and g of x is L. Well, infinity plus some number is just going to be more infinity, so it's just infinity still. and that infinity kind of absorbs that number. Now the product limit is x approaches c of f of x times g of x. And again, remember you break this up and do the limit of each separate product part. So the f of x, that's infinity times L. Well, infinity times L is just a bigger infinity. So your answer is still infinity. Now, notice I put when L is greater than 0. Had L been negative, or a negative number, then your answer would be negative infinity. And then finally, the quotient limit is x approaches c of g of x. Now remember, g of x is a number, L, over f of x is infinity. If you have a number and you divide it by bigger and bigger and bigger numbers, that fraction is going to get smaller and smaller and smaller, so it's approaching 0. Okay. So similar properties hold true for one-sided limits and for functions for which the limit of f of x as x approaches c is negative infinity. Okay. So here's where we're getting into some more challenging problems. And I want to point out, sorry about this mess right here. If you look at these limits, they look normal. They look like limits we could have done in section 1.4 or 1.3. So that's why I think you have to be on alert. So start off like normal. You start off by plugging the number into the function. That's the very first step. And you can actually treat this like two separate limits. So -3, and that's what I've done. I've broken it up into two limits. So this first one's a -3. That's not a big deal. It's the second part is where we have an issue. If we try to plug 0 in, we get 1 over 0. Well, that's not going to work. So can we do anything algebraically? Is this a special limit? No, you can't factor, you can't use a conjugate. There's really nothing you can do. So you have to logically think through this. You can graph it, but if you don't have a graphing calculator or you don't know what the graph looks like, you need to numerically think through this. So 0, think about it as I'm getting smaller and smaller and smaller. So 0.01. So these numbers in the denominator are going to be getting smaller and smaller numbers. And because it's raised to the 4th power, they're positive, smaller and smaller and smaller numbers. Well, if you take a number like 1 and divide it by numbers that are getting smaller and smaller, it's going to explode into a big number. So I can say, since I know that this is smaller and smaller numbers getting smaller and smaller in the denominator over a number, then this is actually infinity. So that might be something worth writing. I know we're going to write it in the next section, but a number over numbers getting smaller and smaller, it's going to blow up to infinity. Right? I'll probably do some additional videos on these limits. So there's little notes I write off to the side to help me when it's getting smaller and smaller. Okay? But -3 plus infinity, well, that's just going to be infinity. And that's your answer. So technically, this limit does not exist, but we can give a descriptor by saying infinity. Now, on B, so at first you might say, oh, if I plug 2 in, that's 0 in the denominator, but realize if you rewrite this, this is one that I could have put in section 1.4 or 1.3. You can actually bring that denominator up and then just simply plug 2 in. So this function's not defined at 2, but the limit does exist, and the answer is 0. So don't throw out all that algebra stuff that we've been doing, those tricks to manipulating your function. It's when you really get stuck, when there's nothing you can do to simplify the function. That's when you're going to have to start maybe numerically thinking through the limit. Okay, so C. So I've used that property where when it's a fraction, you can do the limit of the numerator over the limit of the denominator, and I wrote that here. So the limit of the numerator, just plug 0 in, it's 4. You're good to go. The problem is in the denominator. So 0, as you approach from the right, of negative natural log of x. Okay, so let's see who paid attention in Algebra 2. So natural log of x, that graph looks like this. So the negative in front of it is going to reflect it. So we're looking at a graph that looks like this. So if we're approaching 0 from the right, where are we going off to? The graph looks like this. We're going off to positive infinity. So I know that this is positive infinity. A number over infinity is 0. And notice a number over numbers getting smaller and smaller and smaller is infinity. So you'll need to know that. But notice there was nothing we could do. There was no algebraic way of solving this. We just had to visualize what that graph looked like. So when you were in Algebra 2 and you had to learn all of those parent graphs, this is a good time you actually get to use it. So now on D, limit as x approaches 3/2 from the left of this lovely function. Now don't give up. Tangent, oftentimes it's going to be nicer to break it up into sine and cosine, and we can use our fraction, do the limit of the numerator over the limit denominator. So, and that 4 is just a scalar. You can leave it here with the function, or you can pull it out in front of the limit, which is what I've done. So basically I rewrote tangent, pulled the 4 out in front, and here's what I'm now working with. So limit as x approaches 3/2 from the left. So in this case, it's actually 1. If you plug 3/2 in, 3's cancel, pi over 2 is, and sine of pi over 2 is 1. And then in the denominator, though, this would be a good one to graph so you can see. But when you plug in 3/2, 3's cancels, pi over 2, the problem is that's 0. But if you're approaching from the left, and then you're looking at your cosine graph, you have, and that's where I put the smaller and smaller numbers. Now, technically, this isn't a mathematical what I've put over here. That's kind of scratch work. But these numbers are getting smaller and smaller as they approach from the left, and it's positive. So a number over numbers getting smaller and smaller that are positive is positive infinity. And that happened here as well. Or no, excuse me, happened up here. Here. So 4 times infinity is just infinity. So we had to visualize the cosine graph on this one and what was happening. Okay. Now where you would get in trouble is if you were approaching from the left and the right. If you had a negative from the left and a positive from the right, you can't work with both positive and negative smaller and smaller numbers. And that 4th root up here took care of that for us. It turned all of those smaller and smaller numbers positive, so we didn't have to worry about that. But you should never have that scenario where you have a negative and a positive number getting smaller and smaller. That should not happen. Okay, so here's 2 more. I'm going to move my face up here for us. So for the limit as x approaches 1, now again, break this up into separate limits, which is what I've done. This one is just a ring limit we did in section 1.2. Plug 1 in, done. Now for this one, here's where it gets interesting. I want to plug 1 in, but you get 0 in the denominator. Okay, are there any strategies that I know of I can use? Can I factor, conjugate, multiply by 1? There is nothing. So now think numerically. If I try to plug 1 in, obviously I can't plug it in, but if I plug in 0.09, if I plug in 0.9, or if I plug in 1.01, I'm going to get, so if I plug in 1.01, I get 0.01 squared. So I'm getting smaller and smaller numbers in here, and I'm squaring them, turning them all positive, which is perfect. So if I have positive that are getting smaller and smaller, 1 over smaller and smaller numbers is infinity. So, but be careful, you have that minus sign. So minus infinity then becomes negative infinity. So it works. Now I did graph this one for us. I graphed this part of the function over here, and you can easily see that you're going off as you approach 1 from the left and the right, even though you're not coming together. The limit does not exist. Nobody's saying that, but you are going off to infinity from the left and the right. Okay, so then here's one more. Limit of the numerator, so that you just get 5. And then in the denominator, again, same thing. You have numbers from the right, and it's smaller and smaller numbers, so you actually get infinity. So please do your homework. You've got to practice these problems. These are very challenging. So be open-minded, try your other approaches first, and then look at the graph, but start thinking what's happening with the numbers. You're trying to get that number over infinity or a number over numbers getting smaller and smaller. Okay, so please email me if you have any questions.